Sampling theory. So, sampling theory, we did this quite a while ago now. Some of the key things that we have done so far. Can anybody tell me, first of all, there are two sets of data effectively, and we're looking at the average of each of them. What am I talking about? What are the two sets? Yeah, we were looking at samples and we were looking at population. The population is absolutely everything. The sample is a subset of it. Okay, what notation do we use for the mean of our sample? X bar. Okay, what notation do we use for the mean of the population? Mu. Okay. What notation do we use for the standard deviation of our population? Oh well, you're doing one thing ahead. Yes, just sigma there. Yeah. Okay, and the variance would be sigma squared. Now the central limit theorem. So just put down as the CLT. The central limit theorem from last time told us what? What did the central limit theorem tell us? X bar itself is a random variable distributed
normally with mu and whatever.
Yeah, with a mean of mu and a variance of sigma squared over n. So we said as n gets bigger, as our sample gets bigger, the variance of our x bars, the variance of our sample means, gets smaller. That all seemed to make sense. So x bar itself is a continuous random variable. Okay, right, I gave you some examples. We should now be on this one here. So if you can find this one, we're continuing from before, and I think we are here on example 2. And example 2 was about a dice, where a die wasn't a normal one. It had 3 1s, 2 3s and 1 6. We have previously found its probability distribution to be, as we have done, as we've got here. Okay. And we're looking now at the total score on it being 120. So I'm just going to scribble down here again our distribution. We had the scores can be 1, 3 and 6. The probability it can take each is a half, a third and 1/6. We've already worked out the mean, the expected value of x to be equal to mu and 2.5. We already worked out the variance of x from here by doing sigma x squared p, and take away the mu squared value was 3.25. We have said previously that the sample means we are going to get are normally distributed. But now a total score, and we are rolling it 40 times. I'll put down over here n is 40 as well. The totals. What do we reckon about the total scores? We haven't looked at totals or sums before. But if the mean is normally distributed, what would you reckon about the totals? Sorry? They are normally distributed, yeah. So if you are summing lots of x's, okay, then there also you do get something that's normally distributed. Now we know that each time you do the spinner, you expect to get 2.5 on average. What do you think we would expect to get if we added up all the scores for 40 goes on the spinner? So 40 times 2.5. Yeah, 40 times 2.5. Okay. Now in terms of notation and symbols, what is that 40? What is that 2.5? N times by mu. Yeah. Okay. So that is n times by mu. Now the variance, okay, it's more straightforward than the central limit theorem, the sigma squared over n thing. The variance is just the variance of x times by n. So just like over here, you do the mean times by n, and you do the variance times by n. We weighed out last time, the variance was 3.25, So if I times that by 40 as well, I get here that the sum of x, when I'm rolling the spinner 40 times, is, well, 40 times by 2.5, what's 40 times by 2.5? 100, yeah. Okay. Should be able to do the next one in your head. 3 1/4 lots of 40. 3 lots of 40, quarter of 40 added together. 130, yeah. Okay. So the sum of these scores will also be normally distributed with a mean of 100 and a variance of 130. And the question was saying, what is the probability that the total score is greater than 120? That's a reminder of the question we're trying to answer now. Look at that question, all of your experience about the normal distribution. What do you think you might do to that first of all? Make it a less than, yeah. So do 1 minus the probability that the total is less than 120. Now, is that technically correct, what I've written down? Someone's saying less than or equal to.
Not what matters.
Doesn't it? Why doesn't it matter?
It's continuous random variable.
Is it?
Oh.
Is it?
3.
Is the sum of this a continuous random variable? The sum of this can only be 1s, 3s and 6s added together. So this sum here is not a continuous random variable. The sums is discrete. And this is where you've got to be careful. The sum of these is going to be discrete because it is just made up of adding up 1s, 3s and 6s. So the opposite of greater than 120 is less than or equal to, and there the or equal to bit does actually matter.
Because it has to be the closest one to
Well, think we have done something like this before, because the normal distribution that we're going to use is continuous, but these sums are discrete. What do you think we will have to do? Continuity correction. Yes. Okay, good. So when you are dealing with sums which are discrete, you do have to introduce the continuity correction. So I can say then this is going to be 1 minus the probability that the total, and I'm now using the normal approximation or the normal distribution. Now what am I going to put in here then instead of my 120? 120.5, yes, because I want to include the 120, so I've got to go up above it. And here, this line here now, I am back on continuous territory. So this is just like an good old-fashioned normal distribution question. 1 minus phi of my x value minus my mean, which you said was 100, over my standard deviation, which is the square root of the 130 we had earlier. I've got down here it's 1 minus phi of 1.798. I've got down here, if you phi that, you get 0.9639. So the final answer is 0.0361. Okay? So this example has all the pretty much scenarios you need, and if you can follow this through and work out why we're doing what for each scenario, you should be okay. It's to do with chocolates, and chocolates is to do with their weights. Their weights are W, and W, we are told, the great god of statistics has told us this, are normally distributed with a mean of 10 and a standard deviation of 4. We'll do that in grams. Did I say a standard deviation of 4? I meant to say a variance of 4. So that would be in grams squared for the variance. And they are packaged in boxes of 25 chocolates. And we have 3 parts to this question. Part A is to find the probability a randomly chosen chocolate weighs between 9.5 and 10.5 grams. So W is in grams. Part B, that 25 chocolates together, that's like the box of chocolates but minus the box, 25 chocolates together, that what we want there is a probability that they weigh between 247 and 253 grams. And then part C is looking at the average weight of 25 chocolates.
24.7 and what was it, sorry?
253.
247 and 253. Okay, sorry, that's off the board for those in class, isn't it?
24.7 or 20.
247. Okay. Now, part C, the average weight of 25 chocolates is between 9.9 and 10.1 grams. So, part A is about individual chocolates. Part C is about the total weight of 25 chocolates that will make a pack. And part C is the average weight of 25 chocolates that would make a pack. And it's these three different scenarios and being very sure you know what's going on in each one. That's important. Part A. Anything tricky going on in part A? No, it's a bog standard normal distribution question. Okay? So we want probability that 9.5 is less than W is less than 10.5. We had earlier that W was normal 10 2 squared, or 4, however you want to write it. I'm going to do a little quick drawing. We've got the weights 10, I've got a 9.5, I've got a 10.5. I want between, I want this area here. What's an efficient way of doing that? It's symmetric, yeah, it's symmetric about the mean. So, what could we do?
Just work out one of them.
Yeah, if we just work out this red one here and double it, we will get the two red ones added together. Okay, so because of the symmetry here, which we might as well exploit, what we want is two lots of the probability that W is less than 9.5. Might as well write it as a less than. We like less thans. Okay. So, can I just leave you to finish that calculation off yourself? I'm just going to freeze it for those in class. And I should have put a 1 minus in there, and I didn't. So. Anybody in class have an answer? Go on.
0.1974.
Spot on correct.
Okay.
I didn't say when I was talking to you earlier, it should have done a 1 minus the 2 bits, because we actually want the blue bit in the middle. Okay? So, yeah, there we go for that first bit. Okay? No continuity correction, no central limit theorem, straightforward question pretty much. Okay? Right, next then, on to part B. And part B was looking at the sum of the weights of 25 chocolates being between 247 and 253 grams. And these are making a box. So, if we let B stand for these weights, B for box, okay? What will the distribution of B be? From what we did earlier. Mu times by n for the mean, and sigma squared times by n for the variance. So mu of each chocolate is 10, and there are 25 in the box. The variance was 4, and there are 25 in the box. So now we've got B is normally distributed 250, 100, and we want the probability that B lies within the range 247 and 253. Right. Any comments? Yep, we can do the symmetry thing again here. Is B discrete or continuous? If each of the individual chocolates is weighed in grams, that's continuous. Then here, summing those up, it will also be continuous. So last time we summed, we had a discrete sum, but this really is a continuous one. So I've got mean 250, I've got 247, I've got 253, I want the bit here. So like last time, if I do 1 take away 2 lots of the red bits, I will get what I want. Okay. Any answers? Yeah, 0.2358. Okay. Are we good to carry on? So, part C was asking about the average weight of the 25 chocolates that will go and make a box. So, in notation, what am I dealing with now? Am I dealing with W? Am I dealing with B? It's the average weight. Well, maybe I should have expressed it more carefully at the beginning. It's the average weight of each chocolate that is going to make up the box of 25 chocolates. So it will be W bar, yeah. The average weight of each individual chocolate. And I've got a sample size of 25. And we had earlier that W was normally distributed 10-4. So how will W bar be distributed? Okay. It's the central limit theorem. It's mu sigma squared over n. So it's going to be 10-4 over 25. And we want the probability that the mean weight of each chocolate is between 9.9 and 10.1. Anything we can do to help ourselves here? Symmetry again. We want the blue bits. That's 1 minus the red bits. Okay, I'm going to freeze it here, see if you can go through and get that answer yourself.